So now let's introduce the nucleophiles that we'll be using in this chapter. Chapter 13 is characterized by really strong nucleophiles, which once they're attached to the carbonyl carbon, they're not going anywhere. We're going to see in subsequent chapters, sometimes we'll use nucleophiles that themselves could be good leaving groups, but for now, we're going to be dealing with really strong nucleophiles. So the first set are called, let's see, make sure I'm recording. The first set of nucleophiles we're going to call hydride delivery reagents. These you have seen before for the most part. Hydride is, the term hydride is for H minus. That's not a proton, that's not hydrogen, it is hydride. Hydrogen with 2 electrons is H minus. And you've seen a reagent involving hydride before. Sodium hydride is just an ionic compound of Na plus with H minus. The problem is it's not very soluble in organic solvent. If you stick it in organic solvent, it sits there as chunks or a suspension at the bottom of your flask. And because of that, it's not a great reagent for delivering H minus. In fact, all it is a really strong base. So we will not use NaH as a hydride delivery reagent, mostly because it's insoluble and it doesn't work. Instead, we will use reagents in which the hydrogen is already attached to something. So you've met these both before, I think in the chapter on oxidation and reduction from 351. One of these is sodium borohydride. This is a boron compound attached to 4 different hydrogens with sodium as the counter ion, NaBH4. Borohydride. There are actually many borohydride reagents. These differ in the number of hydrogens on the boron. Many of them, of the borohydride reagents, have carbons, a few carbons in places of some of these hydrogens. As long as you've got one boron-hydrogen bond, you're good to go. The other reagent that you were introduced to is called lithium aluminum hydride. This is the analog of sodium borohydride. It is way more reactive than borohydride because the difference in electronegativity between boron and hydrogen is less than between aluminum and hydrogen. I should point out, if you look up electronegativity scales, that the boron and the aluminum are each less electronegative than hydrogen. So even though the negative formal charge is on the boron or the aluminum respectively, most of that negative charge is felt out on the hydrogens. And because aluminum is even less electronegative than boron, the hydrides in lithium aluminum hydride are more reactive than in borohydride. Okay? So you can think of lithium aluminum hydride is a more reactive hydride delivery reagent than sodium borohydride. Sometimes people in a hurry, you will find organic chemists abbreviate lithium aluminum hydride as La, which is kind of weird. But there you go. The more reactive versus less reactive qualities are illustrated into some practical things that you'll notice in the text but aren't necessarily worth memorizing. One of these is that sodium borohydride is okay in protic solvent, meaning you can use solvents that have acidic protons like methanol or alcohols or water. Lithium aluminum hydride is decidedly not okay in protic solvent. It's reactive enough that in protic solvent lithium aluminum hydride will deprotonate the solvent, generating hydrogen gas. The reaction's exothermic enough that you might start a fire. So you have to be careful with lithium aluminum hydride and avoid water. And there's a lot of things that we do in the OChem lab to do reactions under anhydrous conditions. Let's see. Often preferred solvent for lithium aluminum hydride is ethers. So diethyl ether is often a good solvent. This is abbreviated, if you see this in the text, E2O, or the cyclic analog called THF, tetrahydrofuran. You will see those, you'll wonder what the heck are they. Just come back here and remind yourself, oh, those are polar solvents that are good at solubilizing ionic type molecules, but they don't have acidic protons, so they're not going to start a fire with lithium aluminum hydride. Okay, let's talk about use of these reagents with some aldehydes and ketones. These are your hydride delivery reagents. So you can use them interchangeably with aldehydes and ketones. Here is a boring aldehyde. Here is NaBH4. We could use a protic solvent. I'm going to draw the solvent below the arrow. That doesn't always have to be the case. Sometimes people will leave off the solvent. I'm going to show it so that you can get used to seeing it, because sometimes in the text that will be shown you. The product of this reaction is the aldehyde going to the primary alcohol. I don't recommend that you memorize that aldehydes react with sodium borohydride to give primary alcohols. I don't think you need to if you understand the reactivity of organic molecules and you understand the function of the hydride delivery reagent. Let me show you the mechanism of this reaction. It's only the borohydride reagent that's involved. Boron hands off H- directly to the carbonyl carbon. We have the nucleophile attacking the pi star to give us this, what we might call a tetrahedral intermediate. At that stage, we look at the things that are attached to the sp3 hybridized carbon of the addition product, and we ask, do we have any leaving groups? We do not. None of these are leaving groups, so we are stuck until aqueous workup or until the negatively charged oxygen can pick up a proton from solvent in a simple acid-base chemistry step, and that gives us the product. Okay? So hopefully you can see why I don't think you need to memorize that aldehydes react with sodium borohydride to get primary alcohols. Because if you know what the reagent does, and you know carbonyl reactivity, and you know what leaving groups are, you can look at that molecule and you can predict what would happen. Okay, questions about that? By the way, sometimes when I'm in a hurry, I'm going to assume you guys understand what an sp3 hybridized carbon is. Please do not tell me, are all of those bonds in the plane of the page? They are not, right? You know that that's a tetrahedral carbon. I'm just being lazy, not showing stereochemistry because it's not a stereo center. Are you okay with that? I could be even lazier by not even showing the hydrogens, and that would be okay too. All right, let's do another one. You could have used lithium aluminum hydride interchangeably with this reaction. Let's do another one. This time I'm going to show a ketone. I'm choosing this ketone on purpose because we're going to see the possibility for two different enantiomeric products. We would use lithium aluminum hydride, and we're going to use THF as a solvent. Sometimes a way to control the reactivity of lithium aluminum hydride is to do this reaction at really low temperature. You will see sometimes in the text they might put a temperature there. They're just telling you we're trying to keep this anhydrous and prevent from starting a fire. I'll show you the product of this reaction Here I will use dashes and wedges. You're going to get both enantiomers. I'm going to draw both of them. As you know, I could have also just drawn one of them and then put the plus or minus, or I could have drawn the structure like this, but without any dashes or wedges, and you would have to assume that I meant both stereochemical configurations at that stereo center. The mechanism, you can see that we have delivered a hydrogen as our nucleophile to either the top or the bottom face of this ketone. The mechanism is as follows. Here is the aluminum hydride reagent. One of the, oops, that should be a 3 at this point. One thing your text maybe doesn't point out, but is generally observed in organic chemistry, is that the lithium is coordinating the lone pair on the carbonyl oxygen, thereby activating it for attack. Do you remember in the first half we talked about Lewis acid activation of carbonyl compounds? This is an example of that. Lithium is really, really good as a Lewis acid with oxygen, and so that's another reason this reagent is much more reactive than sodium borohydride. What happens is aluminum hands off H- directly to the carbonyl carbon, attacks the pi star. We break the carbon-oxygen bond. At this stage, we get the following intermediate. I'm not going to show you, I'm going to show you both possible enantiomers of that intermediate by drawing the intermediate this way, just without any dashes or wedges. At this stage, most people think that you could draw the intermediate this way, a negatively charged oxygen associated as an ion pair with the lithium. Some people go so far as to draw that association as a covalent bond between oxygen and lithium, and there's actually really good evidence that that's the case. So you can draw it either way, I don't care. Functionally, they're basically the same. And I think your text probably glosses over this and doesn't point this out. At this stage, again, we don't have a good leaving group, so we're kind of on the sp3 carbon of our tetrahedral intermediate, so we're sort of stuck until aqueous workup. Remember, unlike the conditions above, where we could use methanol in the solvent to protonate the negatively charged oxygen, we don't have any acidic protons in our solvent, so we're done until aqueous workup. Aqueous workup introduces water. You can show the final deprotonation step as follows. The negatively charged oxygen pulls a proton off water. If you want to show that from the other way I drew this intermediate with a full covalent bond between oxygen and lithium, you just take the electrons from that oxygen-lithium bond, rip them away from lithium, and attack the hydrogen, and that gives you the final desired product. Okay? Again, not worth memorizing. As long as you know what the hydride delivery reagent does, you can follow through the consequences. I wouldn't bother memorizing at all that ketones react with lithium aluminum hydride or sodium borohydride to give secondary alcohols. If you understand the mechanism, that part's obvious. All right, questions? So let's do some carboxylic acid derivatives. Let's do some examples where we've got something other than hydrogen or an alkyl group attached to the carbonyl carbon. So let's say we do an acid chloride. Okay? We've already recognized that Cl- as a good leaving group. Let's use lithium aluminum hydride. And again, we'll use an aprotic solvent, a non-protic solvent, to avoid quenching our reagent. We'll draw the mechanism analogously as we have done before. I'm not going to worry about the lithium. I've shown you that once, and it's still probably happening, but for simplicity's sake, I'm going to omit that. Here's the negatively charged aluminum hydride reagent, delivering a hydrogen to the pi star, break the carbon-oxygen pi bond to get the following intermediate. Negative charge on the oxygen. Here's the new carbon-hydrogen bond, and there's chloro. Got a good leaving group, right? The chloro attached to the carbonyl carbon is a good leaving group. Relative to that leaving group, here's the alpha position and the beta position. We have a negative charge at the beta position, so we can do beta elimination, kind of analogous to an E2 reaction. And that will give us an aldehyde product. But what do you know about aldehydes and lithium aluminum hydride? They're reactive too, right? The aldehyde product of that substitution reaction, the substitution reaction with the acid chloride gives me this aldehyde product, but the aldehyde product is still an electrophile. That was ominous. It's almost thunder. If we could get some thunder sound effects, that would be fun. The aldehyde product is still an electrophile, which means that another molecule of aluminum hydride can do the same reaction again, delivering H- to the carbonyl carbon. I'm going to move our chloro leaving group over there since it left. Delivering H- to the carbonyl carbon to give us this negatively charged intermediate, where now I will have added two equivalents of hydrogen to the carbonyl carbon. The blue one and the purple one. Now I don't have a leaving group. Then I'm stuck. I don't have protic solvent, so I'm stuck until aqueous workup. I'm not going to show you that aqueous workup step. I've showed it to you before. It simply involves a negatively charged oxygen on that tetrahedral intermediate picking up a proton from water. Okay. So the acid chloride gets reduced first to the aldehyde and then to the primary alcohol. Why can't we stop at the aldehyde? Two reasons. First, lithium aluminum hydride reacts with aldehydes. Second, aldehydes react with lithium aluminum hydride. And the third reason is you might ask, well, okay, what if I'm really careful and I only add 1 mole of lithium aluminum hydride for every mole of acid chloride? The answer is, in practice, that has never really worked out that well in the lab. As soon as you form some aldehyde, the first aldehyde to form goes on and reacts with another molecule of lithium aluminum hydride, and so you're going to get a mixture of products. It doesn't really work well. So when you use lithium aluminum hydride with an acid chloride, you're going to assume that you're going to reduce all the way, not stopping at the aldehyde, but going all the way to the primary alcohol. Okay? Same thing, yeah, go ahead.
How detailed do you want us to be with drawing the spectator ion throughout the steps?
Spectator ion, the lithium?
Or, no, I guess the chloride.
The chloride is the leaving group. I drew it to show you that it had left, but I normally won't even bother.
And for the aluminum, would you like us to draw it?
The aluminum, once it's gone, what does it do? That's a good question, and there is an answer to that, but I don't care about it. Yep. I'm tempted to tell you, but I'm going to restrain myself. Okay. Other questions? Yeah.
Maybe this is getting
if you added a base, could you slow it down? That would probably just, no, let's see. It's a good question. I haven't thought that through. I don't think it would help. All right. Now, what I'm going to show you now is going to be exactly the same as we did earlier, only we're going to do an ester. Okay? This is a methyl ester, and we're going to use the same conditions, lithium aluminum hydride and THF. I'm going to have you push the arrows for this one. I'm going to show you the intermediates. Good thing I'm not talking, so we can just listen to that. Okay, so lithium aluminum hydride can react with the ester in the same way as it reacts with the acid chloride. The thing to look at this stage, and as I said, I think you can probably, based on what I drew above, now that I've drawn the intermediates, I think you can push the arrows. You should go back and do that to make sure you can do it. The one step in question is this one, because how do you get from that negatively charged tetrahedral intermediate to the aldehyde? The answer is that the ester oxygen, whoops, I wanted a highlighter. The ester oxygen must have left as OCH3 minus, as the alkoxide leaving group. Now you might be uncomfortable with that, and frankly you should be, because you were told a lot in chapter 9 that OH minus or OR minus, negatively charged oxygen's generally not that great at being a leaving group. And that's true. CH3O minus is certainly a poorer leaving group than chloride. However, in this beta elimination step, whether or not a leaving group can leave really depends on how reactive that leaving group is relative to the thing that's kicking it off. I'm going to highlight in orange the thing that's kicking the leaving group off. The thing that's kicking the leaving group off is itself a negatively charged oxygen. Okay? So you can imagine it being reasonable for a negatively charged oxygen, highlighted in orange, to kick off another negatively charged oxygen in pink. Either way, you got a negatively charged oxygen, so the situation didn't change that much. So you would predict that this step would be reasonable and have actually a decent equilibrium constant. One of the things I'm not telling you is that it's actually also reasonable, because we won't get to this till another chapter, for this negatively charged oxygen to attack the aldehyde and to go backwards. We're going to forget that we ever saw that. We're going to pretend that the horror didn't exist. We're going to come back to that. But the point I want you to take is that when asking whether the beta atom can kick off a leaving group, your key question is the thing that gets kicked off more or less reactive than the tetrahedral intermediate that did the kicking? Look at the beta atom. If it's negatively charged, then it's perfectly fine. If it's a negatively charged oxygen, then it's perfectly fine to have that negatively charged oxygen leave. Okay, any questions about that? Okay, so esters, carboxylic acids, react with lithium aluminum hydride. It turns out that sodium borohydride is reactive enough to do ketones and aldehydes, but not reactive enough to do esters. On the other hand, lithium aluminum hydride can react with esters, acid chlorides, aldehydes, and ketones. So you're going to see us use sodium borohydride generally for aldehydes and ketones. You're going to see us use, there I did it because I'm in a hurry, lithium aluminum hydride for both aldehydes, ketones, esters, and acid chlorides. What that means is that you can set up a situation where you can do some selective reductions. So for example, if I were to take this starting material, which has both a ketone and an ester, I could use sodium borohydride to reduce the ketone to the secondary alcohol while leaving the ester untouched. ET there is an abbreviation for an ethyl group. In contrast, if I used the same material, the same starting material with lithium aluminum hydride, I would not be able to selectively reduce the alcohol, the ketone versus the ester. I would expect to have to add enough lithium aluminum hydride that I could fully reduce both functional groups, the ketone to the secondary alcohol, the ester to the primary alcohol. Okay. One other thing about these hydride delivery reagents, this is described in detail in your text. I will not ask you about this mechanism, but I want you to be able to do enough problems in the text to give yourself a challenge. So the following other carboxylic acid derivatives can also be reduced to primary alcohols by lithium aluminum hydride. The mechanism is somewhat problematic, and so the chemistry works, but we're not going to worry about the mechanism. You can reduce you can reduce carboxylic acids and amides using lithium aluminum hydride. If you reduce the carboxylic acid, you get the primary alcohol. If you reduce the amide, interestingly enough, you end up with the amine as your product. I want you to know enough about that you're able to predict the products and synthesis questions. We are not going to worry about the mechanism here. Again, it's a little bit problematic and it just makes things worse to know it, so we just won't know it. Okay. Questions so far? Yeah.
So I'm sorry, on the OET, that you said was a leaving group because the oxygen at one point becomes negatively charged.
Right. In this pathway, we haven't drawn the mechanism here, but if we did, you would go through an intermediate that looked very much like this, where a hydride would have been added to that ester carbonyl carbon. You get a negatively charged tetrahedral intermediate, and then that will be nucleophilic enough to kick off. This is MEO minus instead of ETO minus, but same thing. Yep. Okay, others, yes?
Real quick, can you show the mechanism for last time you showed us LiH4 with that one?
This one? Can I show you the mechanism? Not today. Will I? No. The mechanism exists, it's known. The reason it's problematic is because it's not easy based on the mechanism that's shown to predict what's the good leaving group and why it should happen that way. I have taught it before and students asked me retroactively to not have taught it. So that's why I'm not doing it now.
So do we just memorize that?
That's a memorized one, yeah. Okay. Yes?
So would you say that like sodium borohydride can't do these two, and that one only works with aldehydes and ketones?
Right, we're going to use sodium borohydride just for the aldehydes and ketones, not for the esters. So that gives you some selectivity, some flexibility during synthesis. Yeah.
So it seems like in these agents, like the cation isn't really doing a lot, like the lithium with the sodium.
Right.
So could you also do, in theory, like sodium aluminum hydride?
Right. Is the cation doing a lot? Could you do sodium aluminum hydride? The lithium actually is doing something. I showed you that here. The lithium actually coordinates the carbonyl oxygen, makes a bond with the negatively charged oxygen in the tetrahedral intermediate. And I think there's evidence that the lithium is actually important. I think the corresponding sodium reagent at least doesn't work as well. If it did, I guess we'd have to ask whether sodium or lithium is more abundant in the Earth's crust. In any case, there's not a lot of people selling sodium aluminum hydride. Yeah. Okay. Speaking of synthesis, I've just showed you that with esters and acid chlorides, you can't stop at the aldehyde. You push on to the primary alcohol. But you can imagine that you might want to be able to stop at the aldehyde. It would be a pain every time you want to do a reduction of an ester or an acid chloride to have to make the primary alcohol first and then PCC that thing back up to the aldehyde. That's inefficient. If you don't know what I meant by PCC, you need to go to 352, 351, chapter 12 maybe, and review what that reagent is. In any case, we do have a workaround for stopping at the aldehyde. So there are two reagents introduced that can stop at the aldehyde. These reagents aren't used interchangeably. One of them in your text is generally only used with the acid chloride, and the other is generally only used with the ester. I don't know why that is. It may be a practical thing. There may be reasons for it. They're not elaborated on in your text. I'll want you to know the use of both reagents, and you may just need to memorize why they work this way. So the first reagent is a variation on lithium aluminum hydride, and this reagent is used, as far as I can tell in your text, only on the acid chlorides. I don't know if that means it doesn't work on any other reagent or if that's just what's generally in the literature. As with lithium aluminum hydride, this reagent has an aluminum hydrogen bond where there's a partial negative charge on the hydrogen. However, unlike lithium aluminum hydride, this reagent has 3 oxygens attached to the aluminum, and those oxygens are each also attached to tert butyl groups. The name of this reagent is unpronounceable, so we just draw it and call it good. Probably lithium tris tert butoxy aluminum hydride. So mostly we'll write it out and then point to it and say that reagent there. Which reminds me of the time that years ago we were at IHOP. I think my first son, who's now 20, had been born, and my wife's grandparents were taking us out to breakfast. And there little Nate was sitting in his car seat, just dozing away. And Gramps, Amber's grandpa, was trying to order the Rudy Tooty fresh and fruity plate of pancakes, but he didn't want to say that because he's too dignified. So he said, "Miss, I'll have that." So anyway, so we will use that reagent there to, the Rudy Tooty fresh and fruity reagent, I don't know, to reduce the acid chloride to the aldehyde. The rationale for why this can stop at the aldehyde is that this reagent is less reactive than lithium aluminum hydride. Why? Because you have all these electronegative oxygens now attached to the aluminum, pulling electron density away, making this hydrogen less reactive. Okay? That's the rationale. This is still mostly a memorized reaction. Mechanistically, it's going to do exactly what you've seen before. The hydride delivery reagent will deliver a hydride, attack the pi star, get a tetrahedral intermediate, kick electrons down, kick the leaving group off, get the aldehyde, but there we stop. A second equivalent of hydride does not get delivered. Okay? So that's a good synthetic workaround if you want to stop at the aldehyde. That's option 1 from the acid chloride. Option 2 is going to be to use a reagent. Now this option is generally used with esters. So here is an ester. The reagent here is diisobutyl aluminum hydride. I've drawn it for you before. I hope I didn't draw it incorrectly. I'm going to scroll back up just to, yikes. Boy, we've done a lot today, haven't we? Yeah, close enough. Diisobutyl aluminum hydride, or dibol. Notice that unlike lithium aluminum hydride, this reagent is neutral. So that's one distinction, and it turns out this mechanism is pretty interesting. Your text doesn't show it to you. Your text just shows you the product and says, ta-da, memorize. Because I've talked about Lewis acid activation of carbonyl compounds, I feel like I can show you this mechanism. The lone pairs on the oxygen are going to attack the empty p orbital on the aluminum. That's going to generate the activated oxonium ion, but notice what it does to the aluminum portion of our reagent. Suddenly, because we've got an oxygen-aluminum bond, that aluminum is now negatively charged, which makes the hydrogen attached to it now reactive. Okay? This is like in medicine, sometimes there are molecules that are called prodrugs. They're not the actual active drug compound. Until you take them, ingest them in your body, they get metabolized to something else, and then they're active. This is a similar compound. This is a similar concept. This is a pro reagent, not meaning professional, meaning before. It's got to be activated before it can do something. The beautiful thing is that the reagent itself activates the carbonyl compound, and in so doing, itself gets activated to deliver the hydride. Notice before that step where the oxygen attacks the aluminum, there's no negative charge on the aluminum. The hydrogen's probably not that reactive. Once we make that bond, the aluminum gets negatively charged, and we have this nice intramolecular delivery of the hydride to the aluminum to give us the following product. Somebody was going to say something, weren't they? All right. The hydride gets delivered, and we end up with this intermediate which is actually stable. You can't kick off the leaving group because the thing that would do the kicking, the kicker offer, is not negatively charged. It's bonded to the aluminum. So you're stuck until aqueous workup. Over the course of aqueous workup, through chemistry I won't show you, the aluminum oxygen bond gets broken. The negatively charged oxygen gets released. At that stage, and at that stage only, do we restore the beta kicker offer. Now a negatively charged oxygen that can kick down and kick off the leaving group, and there we get to the aldehyde. The point is that the leaving group doesn't leave until the reducing reagent's totally consumed. So by the time we get the aldehyde, there's no more dibol left. There's no chance for subsequent reduction to the alcohol. All right. So you can use, again, this is probably a memorized reaction. You can use diisobutyl aluminum hydride. That's the reagent. I can't remember whether it's capital letters or not in your text, but that will take the ester and stop at the aldehyde. Okay, yes?
Is the mechanism personal enlightenment and you don't want us to know it, or would you like us to?
Is the mechanism personal enlightenment, or do I want you to know it? Because I've drawn it, and because you can review it on the video, I'm going to say I want you to know it. I won't always say that. Sometimes I'll talk about things from various parts of sciences they have to do with OChem. Sometimes I ask questions about that kind of stuff on the test. I'm always uncomfortable with how to answer the question, is it going to be on the test? Because I know you're very practical people who are very busy. And I know if I say, no, it's not going to be on the test, there is a button that you push that flushes that knowledge away and you never think about it again. For a lot of you, and I don't make fun of that. You have to be practical about what you're learning. If I say it is going to be on the test, I know there's about 25% of you who are going to stress out about it too much. And I don't want to cause undue anxiety. I also don't want to say things that are going to be immediately flushed. So, what's the standard? Well, I do want you to be aware of this mechanism. Is it going to be on the test? Maybe. At what level? Let's just say you want it to appear as though you were in class today and paying attention. Is that good enough? All right, go ahead.
With the previous reagent you showed us, did you say that that one's only used with acid chlorides?
As far as I can tell in your text, yes, this reagent, they only use it in the examples in the problems, they're only using this with acid chlorides. If you mix and match, I'm not gonna give you any problems.
Okay, so we can use that and have that involved.
You can use them interchangeably. Just notice in your text that they probably don't, for reasons they never explain.
Okay.
Yeah.
Would these both be done in aprotic solvents?
Yes, I think so, generally in aprotic solvents. Yeah.
Are these the only two kinds of reagents, like the ester and the acid chloride or acid halide, that we would just stop at the aldehyde with? Or?
These are the only ones we're learning how to stop at the aldehyde with, yes. I imagine there's other chemistry that I don't know, but yeah. Okay. All right, that concludes hydride delivery reagent. Now this is fun because we got 10 minutes left and I'm about to say the horrible thing that happens when you're only got 10 minutes left in a talk or in a class. And now in the second half of the class, in the second half of chapter 12 or 13, we need to talk about carbon-like nucleophiles. Probably what we're going to do now is going to bleed over into next time. It's okay, we're going to get caught up, it's going to be fine. Let's talk about carbon-based nucleophiles. I know you're tired, hang in there, your endurance will build up. Next time you're going to be saying, bring it on. Carbanion type nucleophiles. As with the hydrides, we need a special class of reagents to deliver negatively charged carbons. You can't just pour a flask of CH3 minus into anything. You can't actually buy that. You have to have a reagent that can stabilize the negative charge on the carbon and that is soluble in some organic solvent. So we're going to introduce 3 new carbanion-like nucleophiles. They all involve metals, and so we're going to call these organometallic reagents. All of these involve carbon-metal bonds, but all of them are going to be a way to deliver basically a negatively charged carbon as a nucleophile to a carbonyl molecule. So the first class are called organolithium reagents. These are going to involve carbon-lithium bonds. So that's ethyl lithium. You have an sp3 hybridized carbon, which I'm illustrating by drawing all the things attached to it, and that carbon is attached to a lithium. There is significant covalent character to that bond, but it is fine for you to think of it as, and because we're thinking of it as I'm using quotes, they're not air quotes when you do it on paper, I guess. You can think of this as a negatively charged carbon and a lithium counterion. That's not actually how it is. It's way more complicated than that. But for our purposes, it's going to react as though it were that. The second class of reagents are called Grignard reagents, named for the scientist who discovered them. These are very much like the organolithium reagents, only the metal that's used is magnesium instead of lithium. Now, if you look at the periodic table, lithium, when it's an ion, has a +1 charge. Magnesium as an ion has a +2 charge. So we would expect that magnesium to be bonded to something else. It's usually a halide, a bromine or a chlorine. Sometimes people will just draw this as MgBr together. That's how I'm going to draw it most of the time. That is a Grignard reagent, but you can think of it, again with the quotation marks, as a negatively charged carbon and then a magnesium counterion and a bromide counterion. We're going to see that these two organolithium and Grignard reagents have very similar reactivity. We're going to be able to use them for our purposes. There's a vowel in there somewhere, similar reactivity. We're going to be able to use them interchangeably. When you write interchangeably, is there an E? Interchangeably? Okay, whatever. You're deceiving me. I'm going to go look it up after class. We're going to be able to use them interchangeably. There's not going to be any rhyme or reason. Now, practically, from a practical point of view, there's difference in reactivity and air and water sensitivity for the Grignard reagents versus the organolithium reagents. We're going to pretend that that world doesn't exist. If you go work in the organic lab, you go work for my colleagues, Steve Castle, David Michaelis, Merritt Andrus, Matt Peterson, Paul Savage, you're going to use these reagents. We don't use them in my lab, so I don't actually know. But there are some differences and some reasons why you'd use one versus the other. There is a third class of organometallic reagents called cuprates. These are even weirder. These involve a bond between carbon and copper in its +1 oxidation state, 2 bonds between copper and carbon, a negative charge on the copper, and a lithium counterion. Cuprates are weird. They have weird reactivity. For our purposes, though, it's okay if you think of this as simply being 2 carbon, 2 anions, a lithium counterion, and a copper counterion. It's not exactly that way, but you can think of it that way. These are going to have unique reactivity. There are going to be 2 different kinds of reactions that cuprates can do that the organolithiums and the Grignards can't do. I can't resist with all these quotation marks. Many years ago, it was like 2001, Amber and I were engaged to get married, and what other kind of engaged is there? Am I quoting Pride and Prejudice? I usually quote Star Wars, but now I think I just quoted Pride and Prejudice. Anyway, my aunt, my family lived in Wisconsin at the time, but I had extended family here. My Aunt Dinah, bless her heart, was throwing a bridal shower for Amber. And Dinah is funny. There's so many Dinah stories, which maybe I will tell you later. But she had this tendency to egregiously misuse quotation marks. So on the invitation, it said, "Come to the bridal shower of Josh Price's fiance." Why she had to say that was because most of my extended family didn't know Amber, but they did know Josh Price, which is me. Anyway, in any case, Josh Price's fiance, and then in quotation marks, Amber. If that even is her name. So we still sort of laugh about that. I think she was using it for emphasis rather than for sarcasm, but we often laugh about that. Okay, let me show you, since I've made a big deal out of telling you that cuprates are unique, let me show you the 2 unique things that cuprates can do. And then we'll get to the more boring stuff with the organolithiums and the Grignard reagents. Cuprates can do something with acid chlorides that organolithium reagents cannot. So let's use, and actually the R group on the cuprate can vary, but we're going to continue to use our friendly neighborhood ethyl cuprate. For all of these organolithium reagents, you're going to be using non-protic solvent. We won't emphasize that, but all of these, being basically negatively charged carbons, are highly reactive as bases, and so we don't want any protons available to gum up the works and protonate the reagent and ruin things. The cuprate can deliver a negatively charged carbon to the carbonyl carbon of your acid chloride to give you a tetrahedral intermediate. Here is your new bond between the ethyl group of the cuprate and the carbonyl carbon of your electrophile. We won't worry about what's left over after that happens. Then you have a tetrahedral intermediate with a good leaving group, and you have a negatively charged oxygen at the beta position, an excellent kicker-offer that can kick off the leaving group. Your product from that is a ketone where the thing that, whoops, that's an eraser. The thing from the cuprate that got delivered is now one of the two carbon groups on your ketone. And the thing that's unique about the cuprate is it can stop at the ketone. You might look at that ketone and say, hey, it's got an electrophilic carbonyl carbon. Why doesn't the cuprate add a second equivalent of my carbanion at that carbon? And the unique thing about the cuprate is it can stop at the ketone. In contrast, you take this same reagent with the organolithium reagent, the same starting material with the organolithium reagent, and you indeed do the same type of chemistry. You get the same tetrahedral intermediate, the same kicking off, the same ketone, but you don't stop there. A second equivalent of the organolithium attacks the ketone to give me this tetrahedral intermediate. It's unique because now we have two equivalents of the organolithium reagent that get added. This is exactly analogous to that business earlier on with lithium aluminum hydride reacting with the acid chloride and not being able to stop at the aldehyde. In the same way, the organolithium reagent is not able to stop at the ketone, but goes on to add a second equivalent, and then upon aqueous workup, you get not the ketone, but the tertiary alcohol, and not just any tertiary alcohol, but one in which you have added two of the same thing to that carbonyl carbon. So that's the first way that cuprates are unique. Cuprates can take an acid chloride and stop at the ketone. Organolithium reagents or Grignard reagents cannot. I'm just going to make a note here and put the Grignard reagent there. The Grignard reagent would do the same thing there. So that's a key difference in reactivity that I want you to pay attention to. All right, my clock says that it is now 9:50. You've been through 2 hours. So with that, we will end. I will see you Friday.